Swayam Prabha. Digital India. Educated India.
In the last class, we were looking at how the tires behave during longitudinal run, right? And of course, we started the lateral as well, but we will come to lateral in a minute or maybe after some time. We will look at the longitudinal force development. Through a very simple and very nice model called the brush model. The brush model is very nicely explained by Professor Pajeka in his classic text, Tire and Vehicle Dynamics, which has gone, I think it's the third edition. It's a very nice book, mathematically very rigorous. It would be very nice if you can have a look at many of the mathematical models that are developed in this book on tire mechanics, though we will not be able to go into those models in this course. And we will be talking about very simple models because we have to move into vehicle dynamics and discuss a lot more things on vehicle dynamics. Tire mechanics being extremely important, I am going slow and we are looking at how actually the forces are developed and so on. There was a question just before the class whether we will have some mathematical model in this course. Yes, we are going to do a simple mathematical model, okay, which is going to be called or which is called as the brush model. But there are very complex models that are available for the force development in tires, but we will not, of course we will talk about a very broad, I'll give you a very broad picture in the next class about what are all the tire models that are available for modeling the longitudinal as well as the lateral forces. But this model brings out the physics of the tire behavior in the longitudinal direction. Okay. One of the things that we saw in the last class is that there is a pressure. I'm just summarizing what we did. There's a contact pressure. There's a contact pressure under the this tire, and there is a longitudinal force. In other words, contact pressure can be converted into force and so on, but the total force F is it. So there's a contact pressure and there is a longitudinal force due to which there is a shear. Okay. Now we also saw the difference between braking and traction. So we said that there is a region, there's a region where the tire is going to stick to the ground, and there's a region after which when the shear stresses exceed the frictional mu into Fz, the normal force multiplied by mu or pressure multiplied by mu, then we said that there would be a slip. In other words, if this were to be the contact patch, then there is a region where the tire is going to stick to the ground. This is the region where it is going to stick to the ground, and this is a region where it's going to slide. Okay. When I said slide, remember that these guys are going to just come in a bit, okay, till again equilibrium is reached and so on. So in other words, maximum force that could be withstood is obviously, in a simple model of Coulomb's model, is equal to mu into Fz. Right. what is our goal? Our goal is to find out how fx is developed mathematically, express it, and what is it related to? What is it related to? In passing, we defined what is called as slip, and we will see how the slip actually enters into the mathematical model, and what is the relationship between fx, the force developed, versus the slip. This is the whole idea. So, how do we do this? Simple, by means of what is called as a brush model. These are the bristles, okay, which are sticking out, say for example from the carcass of the tire, okay, and they have a stiffness, let us say lateral stiffness, say lateral stiffness per unit length, which we would call as Cpx, which is the lateral stiffness per mm or unit length. Okay. So, what we are going to do in this derivation is that I am going to find out what is the deformation. So, the first step is what is the deformation of this bristle or this comb of a bristle, which I would call as u. So, once I know what is the deformation, the next thing I am going to do is to find out or multiply this, okay, to find out the force. Which is nothing but the Cpx into u. The third thing I am going to do is to assume a pressure distribution, because one is left hand side and the other is right hand side of the equation. So, I will assume a pressure distribution, which in this case we are assuming it to be parabolic. Okay, assume a parabolic pressure distribution and call it as Qz. The next step, I'm going to write down the equations, but I want to give a broader picture. The next step is obviously, what is the next step? So, once I do it, I have the left hand side of the equation. What is this force? The longitudinal force. And this is the right hand side of the equation. I can find out mu into Qz. Okay. I can find out the left hand side and the right hand side. And then what do? I find out point at which the slip starts or sliding starts. I'm careful to use the word slip because we are going to give a very specific meaning for slip. So, in other words, let us call that as xs. Okay, fine. Yes, this is a Cpx, the longitudinal stiffness. A good question. See, please understand that these bristles have two stiffnesses. Okay, stiffness is, now you know what is stiffness. So, the stiffness is here in this direction. Okay, and stiffness can also be in a direction which is perpendicular to plane of the board, right? So, which you would call as the lateral stiffness. So, which is Cpy. Okay, so Cpy is the lateral stiffness. Oh, sorry. Oh God, say longitudinal stiffness. Longitudinal stiffness, right. So, Cpy is the lateral stiffness. I didn't notice that, sorry. That is the lateral stiffness. Okay. Though usually it is assumed that Cpx is equal to Cpy, it is not so, there is a 50% difference between the two and so on, right. Good. I'm sorry that I hope it's okay. So the point at which sliding starts. Then, as a last step, what I'm going to do is to find out the total force that is in the x direction, which is the sum of the forces that is generated in the sticking region plus the sliding region. Sticking region plus F. So F sticking plus F sliding. Right? So that's the total force. This is how our derivation is going to progress. Clear? The derivation is going to be exactly the same when we look at the lateral forces. We will come to that. The same similar model is going to be used for lateral forces, but I'm not going to derive this in detail. People who are interested in this derivation, which is going to be exactly the same, can refer to a book by Paseka. Actually, he has derived the lateral force and said that it is similar in longitudinal force. I'm going to do the other way about, so that you will have both the derivations with you. I'm going to derive the longitudinal force and then say the lateral force is going to be very similar. Of course, we'll discuss the physics of that a bit later. Just before we proceed, a word of a comment that though we are discussing longitudinal and lateral separately, there are conditions under which you will have both lateral as well as longitudinal forces develop. So, in other words, when you are cornering and braking, for example, cornering and braking, then there is a combined lateral and the longitudinal deformations, and hence there is a force which is both Fx and Fy. Okay. We will mention this as we go along, and again we will not be able to derive that completely, but at least we will just see this like this, okay, and see what are the final equations. Right. So with this background, let's go ahead. So it's always better that before we derive, better that we write down what are the steps we are going to do. Then maths just follows the physics. Right. Okay. Now I'm going to make some assumptions, because as I told you, this is a simple model. So there are a number of assumptions which we are going to make to keep the maths within our bounds. Okay. Let's assume that, okay, this is the figure from Paseka. We redrawn it in order to understand how the deformations are going to take place. Let us assume that there is a point S. This is a point which lies on the rolling, this radius R, okay, which is such that it rolls on an imaginary circle without any slip on an imaginary ground like that. Okay. So in free rolling, yes, the velocity of S in one direction, this direction, which is omega into Re, is equal to the Vx, so it does not slip, point number one. On the other hand, when there is braking or when there is acceleration, the velocity of S is different from Vx, we saw that, okay, and hence there will be a movement of Vs, or there will be a velocity of Vs, which we would call as Vsx. We will see what this definition is in a minute. Okay, Vsx, okay, depending upon the braking or accelerating, okay, it would be one direction or the other. Right? We will use the same thing like the V, which is in this direction for the tire, can be assumed to be V in the opposite direction for the road, and that it is rotating, okay, at a stationary position. Let us assume that there lies a point. There are slightly assumptions here because you may be confused as to about the r's. We are going to make some assumptions. We are going to make, one of the assumptions we are going to make is that these radiuses are so large when compared to the lengths of these or lengths of these bristles and so on, that we are going to write down this in terms of radiuses which we have defined. In other words, we are going to make some assumptions on the radiuses to make again things simple. Let us say that S prime, it is a physical point, it is a point in the tire which moves with the same velocity as that of S, okay, which moves the same velocity as that of S. We assume that these bristles which are sticking out, okay, these bristles which are sticking out, though we have discrete bristles, actually you can assume that they are continuous, but then continuous bristles do not give that physics, and so hence we can do that, and later we will when we integrate it, we will make it continuous. So these bristles have a base, okay, two things, one which is sticking to the, you can call as the tail, which is sticking to the carcass, and the other which is sticking to the ground, right. What is sticking to, so there is a difference between the two. What is sticking to the ground is going to move with the velocity of the ground, and what is sticking to the base is going to move with the velocity of the tire, the tangential velocity of the tire. Since these two are going to be different in braking, and that is what we are going to see now, there is going to be a deformation of these bristles. That is what we said first, that we are going to look at the deformation of the bristles, right. So the first thing first, so let us look at what is Vsx. So Vsx is, as I told you, is the difference between the velocity, that is we will write that as Vx, okay, velocity of the ground, minus omega into Re, and that is where S is sitting, which we can call as R. So let's say VR is equal to omega Re, say, so that Vsx is Vx minus Vr. Right? Okay. Any questions?
What is the difference between slip and slide?
Yeah. Slip is a very technical quantity which we defined in the last class. We are going to define it again. Okay. English word slip means it's slipping, right? In tire mechanics, slip has a very specific definition. Okay. So though you can say that slip and slide are synonymous, okay, so you can use the words interchangeably, in tire mechanics, slip is a definition. I'm going to define that again in today's class, right. Sliding is the word which we use, where when the force exceeds the mu into F, slides, moves, right. So don't get confused between the two. I know this is a common confusion, okay. So I'm going to define slip now, just wait for a minute, right. Now the first thing is that I want to know how this tail has moved, okay, what is that it's moved. So in order to do that, let me introduce a coordinate system with this as the base, this is 0, x is equal to 0, okay, positive in this direction. I know this is a very busy picture, we will understand this picture slowly. So that's a x is equal to 0, and that this is the positive x direction, and that this contact, look at that, this contact patch is plus a and minus a. So that is again a on either side of 0, this is plus a and minus a. Right? Okay. Now the first thing is that since these points here are moving, all these points here are moving with S prime, which is moving with a velocity of Vr, VR, the motion of the base point, okay, the base point, let's say to a point which is x from this point, so which is x from here. In other words, that the base point travels a distance of a minus x, okay, at a time which is equal to delta t. Okay, the base point is traveling with a velocity vr, and hence the base point moves with a velocity, sorry, with at the time a minus x into vr. Right. At this time, this is the base point moves. This is, say, for example, this has moved from here to here. Right. At the same time, the tip of that bristle or the head of that bristle, okay, that has moved a distance of, at the same time, the distance moved by the head is equal to Vx into delta t. All right. So at the same time, the distance moved is Vx into delta t. Right. So you can say that the distance moved from here to here, suppose I say that here to here, this distance, or let me put it like this. Okay, this distance is V, this is a minus x, and this is this distance is equal to Vx into delta t. Okay. So because it's simple, this is not even a figure is required, that the base is moving with a velocity Vr, and hence that's the time that's required for it to move, and the head, okay, is moving with the velocity Vx, and so the distance moved is equal to Vx into delta t. Right? Any questions? Simple. So what is the deformation? The deformation is the of this bristle. At one hand it is moved this, and the other hand that's the distance. So the deformation is nothing but the difference between the two, okay, so that you can write down the deformation u to be Vr minus Vx into delta t. Yeah.
So the point s dash, which velocity is it moving with? Is it Vr or?
It is the same as s prime's velocity same, and Vsx. Okay. So yes, the question may be, is it Re? Is it sitting at Re? What is that? Yeah. So that's why I said initially that we're going to make some assumptions. We're going to say that R is so large that there's a small difference. Okay, it doesn't matter, and that's how we are defining it. Right? Substituting the expressions. So I can write that to be Vsx. What is Vsx? It's nothing but Vr minus Vx, or Vx minus Vr, because it is going to be, just the difference. So let me define that as Vx minus Vr, or sorry, this can be Vx minus Vr, so that's the deformation. That is actually the deformation. That is equal to Vsx into delta t, and delta t is a minus x divided by Vr, so into a minus x. Okay. Since we are considering braking, I have to be careful, correctly we will write. So Vsx into Vr a minus x. Right. Since the deformation is in my coordinate system is positive along this direction, the deformation actually is in the negative direction, so I have to write the deformation to be minus. Okay. I'm going to define two slip quantities. Okay. One of the slip quantities called theoretical slip, sigma, term given by Paseka, that it's a theoretical slip, okay, is defined as this difference Vsx by Vr. okay, so that u can be written as minus a minus x into sigma x. Right? We also define a quantity called practical slip, kappa, which is used by the industry. Okay, usually people in the tire industry talk about kappa, which is the what we would call as the practical slip, is given by minus Vsx divided by Vx. Okay, this also will put minus so that we are, okay, we use the same quantity. There are plus, minuses, there are so many definitions, I'll stick to that definition. So that u can now be written as, okay, sorry, I'll remove that, I'll put a minus there. Okay, can be written as, in terms of kappa as well, okay, you can find out the relationship between sigma and kappa from this, and can be written as a minus x kappa into 1 plus kappa. Okay, so the first step is over. So we have found out the deformation. Okay, I hope my signs are correct, because one other thing is that I am deriving, breaking. If there's any sign difference, I would. Hopefully it's correct, and I'll correct it later. Right. My next step is, of course, finding out the force. We will come to that in a minute. My next step is to assume a distribution for the normal forces. I said that we will assume a parabolic distribution. Okay, so that Qz, very common distribution that's assumed, okay, all through is equal to, so what it should be in terms of total Fz, and in terms of A, so we will write that as 3 Fz by 4A into 1 minus what should be the quantity there. It should be, you can take a guess, x by A whole squared. Okay, so that when it is x is equal to A or minus A, the term in the bracket goes to 0, and so Qz goes to 0. Okay, so it's maximum when x is equal to 0. Right? Okay. So let me now get to Qx. So these two are fine. Okay. Qx is quite simple. So what's the way we write it? So Qx is what? I know the deformation multiplied by the stiffness Cpx, okay, into A minus x into sigma x, or kappa by kappa plus 1 plus kappa. So the point which I was trying to say is that this is what we define as slip. That's why you have to be careful when you use the word slip in tire mechanics, right? Okay. That's fine. So the next step for us is to find out, when does the slip happen? Is it slip? When does the sliding happen? Right? Okay. When does the sliding happen? When does the sliding happen? What do you think? Yes. So mu n. Now Qz I know, Qx per unit length. So Qz. So it should be equal to Qx should be when it is less than q mu q z, there won't be any sliding, and exceeds, it will be there. So, I will write that condition. Is equal to mu into qz Clear? Let us define a quantity called theta, just to make things easier for us to write. Let me define a quantity called theta, theta x, because you can define similar one for
Why are they writing three x at
this is this one. That's the assumption I make as to how contact pressure is distributed, right? So that the contact pressure is like this. Why? Basically because when I integrate this expression, I should get f z. Integrate it from minus a to plus a, I have to get back this expression. Clear? So that's the expression. Let's define theta x to be 2 by 3, let me just write that carefully, 2 by 3 Cpx a squared mu into f z. Okay, let me simplify this expression now. Let me simplify this expression. Can you do that? Let's simplify this expression. Write a minus a squared minus x squared into a plus x into a minus x. Substitute for theta and get me a value of the relationship between theta and sigma x. So, the first thing, let me, nothing great. Let us say that x is the point at which sliding takes place. X is the point at which sliding takes place, right? Let me also call this as 2a lambda following Paseka. It's a fraction of 2a. It's a fraction of 2a. 2a is the total length of the contact patch. Okay, 2a lambda is what we saw as xs. Okay. Now, let's take this expression and write down this expression, substitute for theta and write down what is xs. So, just do that and it's very simple, 3 by 4 mu f z divided by Cpx a squared into, that's the a squared, into a plus xs by a. Right? What I did was just a, this is a plus s into a plus x into a minus x. Okay. My goal is to find out when total slip takes place. When is the total slip takes place? Lambda is equal to 1. Okay, that makes my job easy. Right? Okay. Let me remove this. Now substitute for xs to be 2a lambda, okay, and that's the at the point at which this lambda, I mean, point from the if this is the contact patch, okay, that is what we called as 2a delta. So that lambda is equal to 1, it's equal to 2a. But in terms of our x, note this carefully, there is a difference, right? So that because we are looking at x from that point, from this center, right? We are looking at x from this center. This is at x is equal to 0. So in other words, this point is x is equal to plus a, and that point is x is equal to minus a, right? So let's substitute that in this expression. Xs, okay, is a minus 2a lambda, that's what is x. In other words, that is x, that is a minus 2a lambda, right? And hence I would write sigma x to be 1 by 2 theta x into a plus a minus 2a lambda divided by a, which I am going to simplify. I'm not going to do every simplification, you can do that, and that's why I'm writing it. And hence lambda, the point at which it starts, is minus theta x sigma x. So lambda is equal to right? Okay. I said that lambda is equal to 1 where the complete, the sliding takes place. 2a, this is completely the sliding. So you can write that, so theta x to be plus or minus depending upon okay. Fine. Right. So let us now find out the force Fx. Now let's now find out the force Fx. As I told you before, the force Fx is the force developed in the sticking region plus the force developed in the sliding region. So I can write down xs from my previous expressions, whatever I have done, to be very simple. You can see that f is at omega re divided by v sx into cpx. Very simple, whatever I have done, just substitute that. So Fx can be written as a to a minus 2a lambda lambda is equal to not 1, 0. I think you guys had not. Okay. Lambda should be equal to 0 for this, that's why you get this. Guys, be awake, right? Lambda is equal to 0 is where complete sliding takes place, not lambda is equal to 1, right? So that's why you get theta x sigma x equal to 1, No, good. That's the point. Complete sliding. Sliding just moves like that, right? Okay. What is that I did? Simple. Cpx sigma a minus xc dxc divided plus this one. And x's I have got from these expressions. That's all. Right? Integrate this and I am giving you a final expression. Okay? I am not going to do the integration, it is not a very difficult integration. Okay. So you would notice that this is the expression. Right? You would notice that I can draw fx now in terms of sigma. So now if I now plot fx versus sigma, my graph would look something like this. This is the sigma versus fx. For very small slip, sigma you can assume it to be equal to kappa. The first term gets into picture. Okay. So you can, one of the quantities of interest to us, you will see that later, is always the slope here, which can be approximated, okay, by, if you look at kappa, it's approximated to be 2p, 2cp to a square. And what's this quantity? That's the maximum force, and the maximum force would always, you need not even look at any of these things, maximum force would always be equal to mu into Fz. So this would be mu into Fz. Okay. So essentially, this is a brush model, okay, where we found out the deformations, we found out where the sliding takes place, the place where the sliding happens, and we just found out the force due to just deformation and due to sliding, and then we wrote down a complete final expression, period. Okay. Look at that. This is slightly different from what's given in Paseka as an expression, but I think this is correct. Have a look at it. Okay. Now practically this may not be a straight line, okay, and that's because we have assumed mu to be a constant, but there's going to be heating and there's going to be dynamic friction and so on, and usually the mu here as a constant may not be valid and you would have a drop here. We would talk about that again in the next class, but before that let us now look at the lateral deformations. Any questions here?
When we equated QZ and QX, that is possible when there is no slip, right?
The slip condition at which the slip happens, that's what we said, the condition under which the slip happens is equal to, this is a condition where both of them are happening, is equal to the Qx, okay, per unit length, force developed per unit length is equal to mu into Qz. this multiplied by dx, that into qz is what I had written down there. Okay, so that's per unit length. So mu into qz is equal to the qx developed. When both of them are the same, then that would be slip. Okay, so this may happen, say for example, at this point, right? If it is completely sticking, this is how it would happen. It would look like. When, for example, here is where that excess, where sliding is going to happen, okay, then this guy would actually start slipping, sliding rather. He is going to slide. So this is how it's going to slide. Clear?
Actually, QZ is like the.
QZ is the normal.
It's not.
See, what I am using is nothing but mu into F, or normal force, very well known, is equal to, that's all I am using. Only thing is I am using it per unit length. Right. So whenever, this is actually an inequality. This is not an equality. This is an inequality. Right. So whenever F is greater, it won't slide. That's all. Whenever it's equal, it will slide.
The same derivation for both sticking and sliding, right?
No, sticking is a portion which is before. When it reaches, what we said is when it reaches mu multiplied by this quantity qz, when it is equal to qx, it slides. That is the point by which we found out lambda or xs. Clear? So when they are equal, so in other words, if this is going to be the contact patch, okay, sorry about my diagram, then we said that this is where it is sticking, and this is what we defined as 2a lambda, or this is what we defined as xs, okay, which is equal to a minus 2a lambda. Sorry, I shouldn't say xs, it's 2a lambda, and that if this is the x is equal to 0, and then this distance is what is called as the xs, which is, okay, clear? So we equated it to find out that point at which sliding takes place. So at these points, we assumed that the force is given by mu qz per unit length dx multiplied force, okay, per an infinitesimal length dx, then we integrated it throughout. Actually, it is x into integral xs minus a, which is right. Strictly speaking, I should write it like this. Xs to minus a. Right. Any questions? Clear? Okay. Now let's look at quickly a lateral force development. I think we have to get back to this figure again in the next class. Let's do that in the next class. Apurva has drawn it so beautifully, I feel bad that I have to rub this, and we'll do that in the next class.